Hello everyone, a very good evening. So today we have Prof Zhang Baile as our speaker for the graduate colloquium. Prof Zhang Baile completed his bachelor's and master's from Tsinghua University in China, following which he pursued his PhD from MIT. Now he's associate professor in SPMS. So his research interests include electromagnetic wave theory, invisibility cloaking, metamaterials, and acoustics. Today he'll be talking about Audible Topology, uh, revealing the secret of topological quantum matter with classical sound. So let's welcome Prof Baile.
First of all, thanks to the IAS and the Student Union for organizing this seminar. Over here, I will share with you some of our research about topological acoustics. And I was asked to speak at the level of undergraduate level. Okay, so I assume you have learned basic EM, electromagnetics, and a little bit quantum mechanics. Okay, so today we're going to talk about audible topology, revealing the secret of topological quantum matter with classical sound. I know it sounds very complicated. Okay, so let's put it aside and then first watch a short video. I think it's very nice. Okay, first of all, I forgot to introduce my group. These are my the group members from my group. Dr. Lin, Dr. Yang, they are research fellows, and the other Ya Hui, Hao Ran, Gui Gen, Zihao, they are all sitting over there. Okay, so these are my group members. So let's first watch a short video. This is about a bathtub drain vortex. Basically, it's a very simple. You can see this is just a container with a hole at the bottom. So this is the water level. And later you can see that the water will just flow away through this hole and then form a vortex. Okay, so let's watch it. And there's supposed to be background music. It's not very relevant, but I think it's very nice. You can see the water level is slowing down. All right, because of time issue, let's stop over here. Okay, so you can see that this is a very simple bathtub vortex. Basically, you have a container and then everybody can watch. So this figure appears, I just copied the figure from Feynman lectures, volume 2, okay? So there's a figure showing this vortex over there. So you can see that, okay, you have a container and then there's a hole at the bottom and then the water start to spin like a vortex. All right, so let's first start to try to analyze this vortex, okay? So you can see that if we assume this vortex is a curve-free, satisfy this condition, meaning that the water cannot stand the friction, okay? The water cannot stand this friction, so it must be curve-free. So if you take the curl around it, on this velocity field, it should be 0. So if you take a small element of the water, and you can see that the water, okay, this is because the water goes around in the azimuthal direction, and then you can see that the velocity field must decay as 1 over r. So if you satisfy this condition, then the water velocity should be curve-free. If you take curl across it, then it should be 0. So if you integrate the velocity field around a closed circle, around the big circle, around this axis, and then this integration will give you a constant c, okay, because of the curve-free condition. So you can see that this condition c, this c is so-called circulation of the vortex. Okay, this is reasonable, right? So this is the circulation there. All right. Now, in the short video we just saw over there, so you can see that the vortex will start to swing back and forth, right, left and right. So it's not quite stable. So the one way to make it stable is we can insert a rod into the water and start to spin this rod with some angular velocity. So this way, okay, this way you can see that the water outside of this rod is still satisfy the same condition as the last slide. Okay, it's still curve free. And then if you integrate the velocity around this axis, still give you this circulation, but you need to satisfy the only difference is this velocity field now is in the region outside of the rod. Okay, outside of the rod. All right. So this is very good. And now, so far everything is classical. Okay. So now I'm gonna make an analogy to the quantum world. Okay. So this is very similar to what? To if you consider a solenoid, right? If you consider a solenoid, so this solenoid is infinitely long, so you can confine all the magnetic field inside. But from electromagnetics, we know that outside of this solenoid there is vector potentials, a vector potential there. And then if you learn a little bit about quantum mechanics, you know that outside of this solenoid, the vector potential forms like these circles, right? Concentric circles. And then there's a very famous AB effect, Aharonov-Bohm effect, which shows you that for the vector potentials, you can disturb the phase of these electrons. So if you shoot two electrons to go from one to go from the left, the other go from the right, they will pick out different phase and start to interfere. So this is so-called Aharonov-Bohm effect. Okay, so this is a quantum effect in the quantum mechanics arising from the vector potential A. And then let's make an analogy here. So you can see that over here, this velocity v is very similar to the vector potential outside of this solenoid. Okay, v. And then if you do the integration around this axis, this c is very similar to the magnetic flux inside, confined inside this cylinder. Okay, all right. So this is the analogy between the AB effect and the bathtub vortex. So the first one who saw this analogy is Michael Berry. Okay, so if you learn quantum mechanics, you know that okay, there's a very famous guy called Michael Berry who developed this so-called Berry phase, and this is one of the major one of the major developments after 1980. Okay, in the basic theory of quantum mechanics. So you can see that this is what he has found is that this is the top view of bathtub vortex. There's a hole at the bottom. Okay, this is the top view. So if you launch a water wave from right, and then you can see that you will, because the rotation of this vortex, you can see that the water wave will pick up a phase difference, a phase dislocation after this vortex. So you can see that they start to interfere. Okay, and then from the figure you can understand whether this vortex is rotating clockwise or counterclockwise, right? Can you? So you can have a guess. You can guess which direction is this vortex rotating around, whether this is clockwise or counterclockwise. This is a top view, okay? This is a top view of the vortex. And then the water wave is launched from the right. This is the only experiment I saw from Michael Berry. Clockwise or counterclockwise? No one, no one wants to have a try. Actually, you can see that over here, the wave going in the lower path is moving faster, right? It's moving faster. So you can see that this vortex is rotating clockwise. Okay? So therefore the water wave going in the lower path and the upper path, they pick up a different phase and then start to interfere. And then give you this AB phase like, AB effect like phenomena. Okay? So this is the bathtub vortex. All right. Okay, you can see that one vortex has already been analyzed by Berry, okay, a long time ago in 1980. And then, okay, remember that here in 1984, Berry proposed his very famous Berry phase. So you can see that this experiment must have given him a lot of inspiration, okay? So what can we analyze? Let's analyze a lattice of vortices, okay? So we assume that there's a lattice, a bunch of rods, and all of them start to spin at the same time, okay, in the same fashion. We try to analyze this case, but it turned out that it's quite difficult because it's actually not a periodic system. What does that mean? That means that you cannot apply the Bloch theorem to get a band structure from it, okay? The reason is because, okay, this is not the vector potential eventually will go to infinity and end up start to blow up at infinity. So what we're going to do is, okay, let's try to confine the vortices. Okay, we study lattice with confined vortices. So we say that for each rod, we can design a wall around it. Let's say this speaker, right? Speaker, there's some materials, some cloth, some coverings, materials to prevent the wind, but you can still penetrate. You can still let the sound penetrate through. So these kind of walls, they can stop the wind, stop the air velocity, but you can still allow the sound to penetrate. So from here, you can see that for each unit cell, because the rod at the center starts to spinning, and then you can see that there's a wall there to confine this vortex. And this actually corresponds to the very classic so-called cutter flow. So this can be solved from the Navier-Stokes equation. There are not many analytic solutions for Navier-Stokes equations, and this is one of them. And actually, from here you can see that the velocity of the air starts to decrease. It's maximum close to the inner surface, and then you can see it start to decrease and then reach 0 at the outer boundary. All right, and now you can start to analyze this. Here I just list a few symbols. Okay, this is a standard procedure to analyze acoustic waves. And then you can start from the Euler's equations and continuity, and then start to get the so-called master equation. Amazingly, okay, this kind of work was done in 1990. Okay, so you can see that this equation is to describe the acoustic waves in a general situation where the background is moving. Okay, so this work hasn't been done until 1990, and then you can change the variable. Okay. You let this phi, this big phi, to be this small phi times square root rho. Rho is the density of the fluid. Over here, this is air. And then you can convert this equation, this master equation, which is done in 1990, to the Schrodinger type equation. Over here, you can see this A, this V. So what does that mean? That means that if we really have this bunch of lattice, this bunch of rods in the lattice, right, and all the rods start to spin, then from the viewpoint of the acoustic waves, it looks like this acoustic wave behave like electrons in a magnetic field. Okay, all right. But so far, where's topology, right? All right. So let me introduce a little bit about the vector potentials. Okay, in the K space. So we all understand that. Okay, if you have learned a little bit quantum mechanics, you know that there's a relation between the momentum p and the position. Okay, so the p is just minus I h bar partial r, and r is just I h bar partial p. So there's a relation between the position and the momentum operators. Okay, in quantum mechanics. So for simplicity, we also know that this p momentum can be represented by h bar times the vector wave vector k. So we just simply write it as k equals minus I partial r, and r equals I times partial k, just for simplicity. Okay, there's nothing special over here, just a simple shortcut to write it. And now, but this is okay. We all understand this. Okay, based on a simple basic quantum mechanics. But this is only in the continuum space. What if we study the lattice? Okay, what if we want to show the electron behavior in the lattice? And then you can see this R is equal to this operator is equal to I times partial K. You need to add one more item here. Okay, you need to add one more atom here. So what is this item? Well, again, I'm going to make another analogy. So if you think about a charged particle in an external electromagnetic field, okay, in the external electromagnetic field, we understand that the vector potential in this case, will enter the Schrodinger equation and then start to change the momentum. Okay, we start to change this momentum through this so-called minimum coupling. Okay, this is from quantum mechanics. So if you compare these two equations, this equation and this equation, you can see that the missing item over here is very similar to this vector potential in this case. This is for a charge in the EM field. Okay? All right, so you can see that there is some analogy there. So if you work through this math, and you can see that this missing item over here is actually another A. Okay, this is this is a very special writing A here. This is so-called Barry connection. I understand this is a very strange writing, but just treat it as a number. So you can see that this is a buried connection. This buried connection is very similar to the vector potential in a EM case, in the charge in the EM case, okay, EM field. So now let's compare these two cases. One, on the left-hand side, this is vector potential, the vector potential in the real space. On the right-hand side, this is a vector potential in the K space, in the moment space. So all of us have learned that this vector potential A, if you take the curl on it, this will give you the magnetic field B field, okay? And similarly, on the right-hand side, this buried connection, we just said, okay, this buried connection is similar to the vector potential. So if you take the curl on it, this is in a vector in a K space, moment space. So it gives you this so-called buried curvature. Buried curvature is similar to the magnetic field. Okay, similar to the magnetic field. You can say this is a moment space. This is a moment space version of the magnetic field. And then on the left-hand side, for this magnetic field B, the real magnetic field, if you take a closed surface, okay, if you take a closed surface and then integrate this magnetic flux, okay, going through this closed surface, then according to the Gauss law, right, Gauss law for the magnetic field, it shall equal to the number of magnetic charge. Okay, if you find it difficult, just think about the electric field version. Okay, this is how you're using the Gauss law to calculate the electric charge, right? So you can see this magnetic charge over here is discretized. You only have one charge, two charges, so on and so forth. It must be an integer. Okay, so similarly on the right-hand side, this is a buried curvature. You integrate this buried curvature over the whole Brillouin zone. Let's say a 2D Brillouin zone. This is a 2D Brillouin zone. A 2D Brillouin zone can be treated as a closed surface. Why? Because the boundary is periodic. So let's say if you take this 2D Brillouin zone and then you connect the left and the right boundaries, you connect these left and right boundaries, and then you further connect the upper and the lower boundaries, then you can form a donut. Okay, so this donut is a closed surface. Indeed, you can integrate this buried curvature through this closed surface over there. And then you can apply this Gauss law, right? So everybody understands this Gauss law. So you can see the result, again, is a discretized number, is a 2 pi c. C number is an integer, okay? It must be an integer. So this corresponds to, we call it a topological charge. And this number also has another very famous number. This is called Chen number, okay? This is named after the great Chinese mathematician Xingsheng Chen, who passed away in 2004. And then the derivation of Chen number was graved on his tomb, okay, on his tomb. And it's located in Nankai University, okay? So you can, if you go to Tianjin, you can take a look. All right, so this is about Chen number. Okay, we all, I think all of us have heard that in 3 years ago, the Nobel Prize in Physics was awarded to 3 pioneers called Thouless, Horden, and Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter. And nobody understands what they are talking about. Right? So actually, when the Sweden Academy of Sciences announced this award, right? You can see that the Prof Handsome, they use this pretzel to explain the award. What is topology? Okay, so you can see, oh, this is one hole over here. This is 2 holes. There's no hole there. Okay, so 1, 2, 3. Okay, this corresponds to a Chen number. Okay, but this is for laymen. But we are scientifically educated, right? So we understand what is Chen number. All right. So what's the use of Chen number? So what is topological quantum matter? So let me give you one example. You must have heard a lot about so-called topological insulators. So what are they? So let's consider this trivial insulator. We say, okay, let's consider the boundary between a trivial insulator and a topological insulator. So we say, because both of them are insulators, so you can see that both of them carry this band gap. Okay, the band gap is a way you can use to distinguish insulators from conductors, right? So you can see that both of them carry this topological carry this band gap, but the topological insulator, for the topological insulator, this band gap is topological, meaning that it is associated to some, let's say in this case, this is Chen number. Okay, so this band gap has properties that is linked to this number, which is 1, 2, 3, 4. So this is topological. For the trivial insulator, this number is 0, so the Chen number is 0. Okay, so in that sense, this is it's topological in the sense that you cannot continuously deform from this region to that region because the topology is different. So you cannot, now if you go through this boundary, okay, if you really go through this boundary, you are not allowed to continuously deform from this band gap to that band gap because they belong to different topology. Okay, so over here, there's, okay, if you think of a ball, right? Ball has no hole, the number of holes is zero. But over here, this is a, let's say if you consider it as a donut, then the number of holes is 1. So you cannot continuously deform from a ball to a donut unless you pierce through, you tears and then pierce through this ball to make a hole at the center. Similarly, over here, you cannot deform from this band gap to that band gap because they are topologically different. So the only possibility is that when you arrive at this interface, you close the band gap and then reopen. Okay. In other words, you need to first destroy the previous topology and then create a new one. Okay. So that's why at the interface, at the surface of a topological insulator, the surface of a topological insulator is conductive. Okay. So the topological insulator is a special material which is insulating in the bulk, but it conducts electricity on the surface. Okay. So this is why the topological insulator must be conductive at the surface. This hasn't been found previously. So let's get back to the acoustic version, our lattice of spinning rods. So this is the spinning rods. So we have the topology there. And actually, if you calculate the band structure now, because all the vortices they are confined, you can apply the Bloch theorem and get a band structure. So if all the rods, the spinning speed is 0, you don't spin them, okay? They are stationary. Then you can see that you can construct Dirac point at K and at this K and K prime at the corners of the Brillouin zone, okay? And then when you start to spin these rods with some finite angular velocity, you can open a band gap over here and then assign non-zero Chen numbers to this lower band and upper band. Okay, this band over here, this band is, the Chen number is 1. This corresponds to the integer quantum Hall effect. All right, so now what's the special point here? So now you can see that, I told you that for a topological insulator, the bulk is insulating, but the surface is conductive. So indeed, this is the case. So you can see that this is a so-called, you can call it an acoustic crystal, or you can call it a photonic crystal, doesn't matter. So you can see that in the bulk, this is insulating, so there's a band gap there. At the surface, this is conductive, so there you can use it to guide the wave, surface wave. So if you put a source, this is the acoustic source, you can launch an acoustic wave to propagate all the way to the right-hand side. And you are not allowed to come back. Okay, you are not allowed to come back. This is so-called topological protection, even if you meet obstacles. First of all, let's say if this acoustic wave meets this cavity and remove a few rods to form a cavity there. So this wave will just go around it and then keep going. Okay, so this is the first defect. The second one, let's say you construct this step. Okay, again, the wave will just go around it and keep going because you're not allowed to come back. And even if you have sharp corners, the wave will just go around it. So this is indeed very similar to the quantum Hall effect, okay, because of the non-zero Chen number. So this is the first topological phononic band gap, okay? All right. Okay, so because we have mentioned phononic crystal, so let's take a look at this sculpture, okay? This sculpture has a name, it's called Kinetic Art. It's designed by a Spanish artist. Okay, so it's located in a public park, and this artist has already passed away in 1985. Okay, apparently, when he designed this sculpture, he didn't know anything about phononic crystals or topology. But in 1995, 10 years later, there are some material scientists, okay, who went there and then measured the sound transmission through this sculpture. And then they found that there's some dips there. So this is the first experimental evidence of phononic band gap. Okay. All right. So my point is not about this the history of phononic crystal. My point is this sculpture has a name, Kinetic Art. Okay. Or it's supposed to be kinetic, but it's not because it's still stationary from the physics point of view. Okay. From the physics point of view. So my point is, if all the rods is really kinetic, if you really start to spin them at the same time, you will see not only a phononic band gap, you will see a quantum Hall effect. You will see a topological edge state going around, okay, for the sound propagation. All right? Okay, so this is just a coincidence, okay? So after that, you can see, this is a lot of researchers, they have proposed their new designs and studies about topological acoustics. So there's an emerging field called topological acoustics, okay, in the recent years. All right, so this is the first part of my about how to introduce the artificial magnetic field for acoustic waves. Okay, the next approach I'm going to talk about is using acoustic resonators. So acoustic resonator is very simple. Let's say this is a Helmholtz resonator, of course designed by Helmholtz. So these acoustic resonators, you can use it to calibrate the tone of musical instrument. So very simple. If you consider a water bottle, okay, this is a water bottle empty. So if you blow through it, you can start to make sound, okay? Okay, and then if you pour water into it, okay, if you pour water into it, that means the cavity has decreased the volume. Then the sound is supposed to be changed. Okay, so this is a Helmholtz resonator. So you can design different shapes, okay, with different shapes to calibrate the tone of musical instruments. Okay, so what we are going to do, actually each resonator can be treated as an artificial atom. Okay, if you think of it this way, if each resonator is treated as an artificial atom, and then you hook them up to form a lattice. Let's say this is a acoustic resonator, another one. This is a unit cell. So if you can hook them up to form a hexagonal lattice, then it looks like a graphene. Okay, and then you can have a Dirac point at the center. I mean, at the corners of the Brilliant Zone. Graphene itself is a Nobel Prize in 2009. Okay, so it's famous for the Dirac points at the corners of the Brilliant Zone. And basically, you can treat graphene as a 2D electron gas. So if you apply a magnetic field, you can observe quantum Hall effect even at room temperature. Okay, but we don't have real magnetic field for acoustic waves, but you can construct an artificial one. So let's say you have a 2D lattice, hexagonal lattice, graphene-like lattice of acoustic resonators, and you apply strings in 3 different directions, try to distort this lattice in a special way. Then you can construct an artificial magnetic field which is uniform in the whole lattice. So it looks like the acoustic wave behave like electrons that is exposed to the uniform magnetic field. So we know that for 2D electrons, if you apply magnetic field, the energy level for the electrons will be quantized. Okay, this is so-called Landau levels. It is actually discovered by Landau when he was only 23. Okay, very young age. But anyway, we don't have electrons. Okay, we don't have quantum electrons, but we have string. We have this lattice. So if you distort the lattice this way, then you can see that you can construct this very flat energy level. It looks like these Landau levels. Okay, so you can construct an acoustic version of Landau levels. Okay, no problem for it. All right, so this is for acoustic Landau levels, and when we really did the experiment trying to dig these holes, you can see that there are a lot of holes in this metallic plate, and then we also distort it. And then after we have obtained some preliminary data, we found that there are already some papers posted on arXiv. So eventually, this experiment was scooped. Right. So let's do something else. What is this else? Okay, I have talked about topological insulators. So if you think of a three-dimensional topological insulator, which is insulating the bulk but conductive on the surface through the surface states. Now it's not edge state, now it's surface states. There's a very fundamental principle, so-called bulk edge correspondence, which means that if you have the bulk topological invariant, okay, this is how to say a topological number associated with this bulk, and then at the surface there will be topological surface states, okay. But recently there are some theories predicting that it is possible to create so-called high-order topological insulator. So in this case, the surface is gapped. The surface is also an insulator, okay. But the boundary of the boundary over here, the boundary of the boundary is this edge is topological. You can exhibit some topological states. Exhibit this edge states. Okay, so this is second order. This is second order topological insulator. You can also make this edge gapped. Okay, or you can also make this edge as an insulator as well. But in this case, you will carry these corner states at these 8 corners. Okay, this is so-called third order topological insulator. All right, and then this involves the first proposal involves the polarization. This is the concept from electromagnetics. So we have dipole, we have quadrupole, we have octapole. Dipole, over the past decades, people have already analyzed it and found that dipole moment can be quantized in the lattice, in the crystal. But it has not been extended into quadrupole and octapoles. This has been done only 2 years ago. And then very quickly, this octapole implementation has already been realized in the following 2 papers. But this is for the octapole. Okay, this is for the quadrupole. Sorry, for the high order topological insulator. So what we are going to do? Let's do a dipole version. So we construct these acoustic resonators and hook them up inside this Kagome lattice. Kagome lattice is like this. Okay. So you can see that the unit cell itself contains these upward triangles, okay, upward triangle. And then there's a downward triangle there. So we assume this upward triangle, the coupling inside this upward triangle. By the way, the inter-atom coupling can be tuned by just adjusting the radius of these waveguides. You can construct these little waveguides to couple these artificial atoms. Okay, and then we assume this coupling inside this upward triangle is T1, inside this downward triangle is T2. Okay, this is a unit cell, and you can calculate the dipole moment. This is polarization in the inside crystal. Using this, okay, it's very similar to the Berry connection. And then this is so-called 1S center over there. This 1S center is another topological invariant, okay, special topological invariant. This is quantized by mirror symmetries. So basically, there are 2 cases. First one, if T1 is larger than T2, you can see the barrier center is located at the center of this upward triangle. And then if T1 is smaller than T2, you can see this center is located at the center of the downward triangle. So there are only 2 choices, okay? There are only 2 choices. So let's first take a look at the first case when these 1S centers, they are located at the downward triangle, okay? Downward triangle. 1S center, the physical meaning for the 1S center is the expectation value of position of the electron inside this lattice, okay? So you can see that you can treat these centers, these 1S centers as the position where the charge start to locate. So this, of course, this is the infinitely large lattice. We want a finite structure. So let's first cut a triangle of this lattice, infinitely large lattice. Okay, this triangle along these 3 cuts. So you can see that along this cut goes through these 1S centers. So what does that mean? That means when you go through this 1S center, you will start to what? You will peel the charge off the shared two atoms. So there will be charge start to remain at this side. Okay, so you will have edge state, and over here at the corner, because you cut through this 1S center, you will expect to see the corner state as well. Okay, so in the experiment, we implement this structure. You can see this is a very simple structure with a lot of holes. Okay, the artificial atoms, and then you just move one speaker, a microphone at the center, at the bottom, and then another microphone to probe it. So this way you can measure the density of states over the whole structure. Okay. And then you can see that very simply, you can construct, you can experimentally measure, okay, the corner states, the edge states, the two bulk states, okay, at different bands. So this way you can verify that, oh, this is the use of one-year centers to predict the corner states and the edge states as well. Okay, let me get back to this figure. These are the locations of one-year centers. Previously, I have already shown it on the last slide. But you don't need to cut it this way, right? You don't need to cut this big triangle off this lattice this way. You can also cut it, let's say if you cut this parallelogram, okay, this parallelogram, and you can see that these two cuts, these two edges are very similar to these two edges of the triangle. They are similar, they're the same basically. But you can see that these two edges, okay, they are different because these two cuts, they don't go through one-year centers, okay? So you can see that these two edges will not carry any corner states, edge states. And then for this corner, there will be no corner states. Also for this corner. You only have one corner that can carry the corner states. So we build this example, and then you can see that indeed there's only one corner states, and then there's two edge states at these two edges. Okay? Okay. I just mentioned that this is only one case when T1, okay, when the one-year center is located inside the downward triangle for T1 smaller than T2. So if you rotate this whole structure by 180 degrees, okay, to put it upside down, that means you have tuned T1 to be larger than T2. That means the one-year centers now is located in the upward triangle. This corresponds to a topological transition. So that means this edge state that is located at A will migrate to C. Okay, will migrate to C after a topological transition. Okay, so C is possible to get a corner state. But even if you have done this kind of topological transition, this corner B1, B2, still they don't have corner states. Okay, so you can see that these corner states, they are shape dependent. Okay, all right. We also have okay, another topic is about Weyl fermion and the Weyl semi-metal. Weyl fermion, anyone know this guy? Anyone know this guy? Nobody. So we all know that at Princeton there's a very famous IAS, same for NTU IAS. Okay, the Princeton IAS. When the IAS at Princeton was established a long time ago, they decided to hire three people, okay? Only 3 people. In physics, of course, it is Einstein, okay? In computer science, it's von Neumann. In mathematics, it's Weyl, okay? So he found a solution, a massless solution to Dirac equation, and then this corresponds to a new fermion, a new type of fermion called Weyl fermion. This is a massless solution for the Dirac equation. And for a long time ago, people thought that neutrino might be a type, might be just the Weyl fermion, but it turns out not, because neutrino eventually still have some mass. So it's not. So this Weyl fermion still hasn't been found in reality. But recently, people have found that in condensed matter, you can construct these so-called Weyl points, and around these Weyl points, the low energy excitations behave like quasiparticles, right? These quasiparticles are very similar to the Weyl fermions. Okay, they can exhibit very similar properties, similar to the Weyl fermions. And then what is also very special is for these Weyl points themselves carry non-zero Chen number, okay, topological charge, +1 and -1. This corresponds to the chirality of Weyl fermions. And then, okay, they always occur in pairs. One is +1, the other is -1. So if you project these two Weyl points, onto one surface, okay, these are projected Weyl points, they form surface states. And then in the momentum space, this surface states connect these two Weyl points together, okay? So they form this so-called Fermi arc. So it looks like, okay, the kidding words, this is where electrons kiss in the momentum space, okay? All right, these are the very hot topics currently in the condensed matter physics. So Weyl fermions and Weyl semi-metal have been discovered in 2015, okay, in this paper. This is a science paper published online in July 16. And then This is a paper in the Physical Review X, submitted in July 15, and then published 2 weeks later. So you can see this competition is very intense. And actually, in the same issue of this science magazine, there's another realization using photonic crystals. Okay? This is implemented at the microwave frequency. Okay, so this is what happens in 2015, in July, around July. And then quickly, there's a proposal for acoustic implementations. So using these acoustic resonators. So this is done by Prof. C.D. Chen in Hong Kong University of Science and Technology. So this is in September, okay, September. So basically, they have proposed 2 designs. One is this is like a graphite structure. The other is a chiral structure based on the graphite 3D structure. So these two designs have different band structure. One is like this, the other like this. Okay, I don't want to go into details, but let me just mention them first. The difference there. Okay, and now you can see that in November, okay, 2 months later, there's another paper, okay, appearing in Nature, talking about a new waypoint and call it type 2. So why this is type 2? Type 1 waypoint is like, if you think of a Dirac point is twofold degeneracy, where you have a point at the band structure. In 3D, this kind of twofold degeneracy corresponds to this point over here. So you can see that at this point, okay, their density of states is 0. It's vanishing because this is just a 1 point. But if you strongly tilt this waypoint, this wave cone, in a specific direction, then you can see that you can form this kind of situation where this waypoint is located between the electron and hole pockets. So that means at this point, the density of states is finite, it's not 0. Okay? So this is fundamentally different because you cannot diabatically connect this point back to this type 1 point. So this type 2 point has been missed by Will in the original theory. Okay. All right. So if you look back at this acoustic structure, the first one is already type 2, but at that time people didn't realize this is a type 2. Okay. So only the surface states of type 1 waypoint is analyzed. Okay. Prof. Chen at that time they consider that these 2 systems are the same, but actually not. So what we do is, okay, let's try to analyze the type 2 waypoint. And then we also want to construct this waypoint from scratch, from 1-dimensional case. So we start with this 1-dimensional case. This is so-called SSH model. Basically, it's a chain of acoustic resonators, but the coupling is dimerized. So you tune the coupling to be strong, weak, so on and so forth. Okay, so this is a 1D dimerized chain. So this dimerization gives you a quantized number. This is called Z phase. So if you put these 2 chains with different Z phase can only have two numbers. Okay, with different Z phase, and put them together, you will induce an edge state at inside the band gap. Okay, so this is the simplest 1-dimensional topological case. Okay, let's move further. We have already realized this 1-dimensional topological phase, and then we extend into 2D. We start to construct. We link this dimerized chains. We link this dimerized chain along the y direction, and then form a 2D lattice. So in this case, you can tune these couplings. Okay, there are some Hamiltonian mathematics involved. Okay, it's just treat them as numbers. So you can see that you can construct these 2 points. These are the Dirac points. And then you move another one in the 3rd dimension to construct a 3-dimensional structure. There's a 3-dimensional structure. And then you can see that you can construct these 2 degeneracies. Okay, these degeneracies. This degeneracy corresponds to the type 2 waypoint. Type 2 waypoints. So basically, in the 3D structure, this is a 3-dimensional Brillouin zone. You can see that you can construct these 4 waypoints. This is a minimum number of waypoints. So there are 4 waypoints inside the Brillouin zone. Okay, plus, minus. So if you project these waypoints onto one surface in the x minus y direction, you will have these 4 waypoints. And then you construct, let's say if you take this cut, meaning that you scan this moment space, you scan the moment space along the kz direction, along this kz direction, and you can see this is the band structure. You can see that this is when you scan the kz. So you can see along this cut 1, you can see this band gap is, you will have, first of all, you will have a band gap. This band gap is incomplete. Okay, so it's very different from previous cases. Okay, first of all, this is an incomplete band gap. And then inside the band gap, you will have edge states. Okay, this is the green color, this blue, this red and green color. They represent the surface states at different surfaces, at the bottom and the top. And if you scan the Brillouin zone along this cut 2, and you can see that, again, you have an incomplete band gap, but you don't have edge states there. You don't have surface states over there. So if you collect all the surface states and then plot them in the momentum space, you can see that they form the Fermi arc to connect these waypoints with positive and negative charges. Okay, so this is the first surface states analysis of the type 2 waypoints in acoustics. And recently, there are also a new proposal, okay, to propose different unconventional quasiparticles beyond the whale and the whale fermions. Dirac and the whale fermions, they are twofold degeneracies. And especially for whale point, I told you that they carry the non-zero Chen number, which is topological charge. But over here, one very special case for this non-conventional quasiparticles is that you can have threefold degeneracy. Okay, you can have threefold degeneracy as well. And this kind of quasiparticles, they don't have counterparts in the field theory, so they cannot be described. They cannot be described by the field theory. Okay, and then for this threefold degeneracy, you can see it carries 2 topological charges, meaning that the Chen number is 2. So over here, you can see from one point you can induce 2. Well, you can induce 2 Fermi arcs at the same time to connect them. So we start to implement this to realize as an acoustic system. Okay, so this is a very nice photonic crystal. Okay, so this is done by a 3D printing. So the real example is like this. Okay, this is a 3-dimensional structure, which is over here. And then, okay, the real structure is much larger. This is just a mini. This is just a simple version. Okay, the mini version of this structure. But the real example in the experiment is this large. Okay. All right, and then you put a speaker underneath, and then insert a microphone into the structure to probe the acoustic wave. Okay. So after you have done a Fourier transform, you can get the whole band structure. So this is simulation and experiment. So you can see indeed you can form a twofold degeneracy which carry topological charge 2. There's another fourfold degeneracy over here. This also carries topological charge 2, but this is a kind of Dirac point. Okay, not the threefold degeneracy. So you can further scan the surface states. Okay, you can further scan the surface state because this is an acoustic wave, very simple to measure. These 2 lines, they are from the experiment, and these 2 lines, they are from the simulation. So basically, you can see that with a frequency from low frequency from 10.3 kHz all the way to 13 kHz. So you can see that this is the surface states in the momentum space. I told you that this threefold degeneracy has topological charge of 2, which will excite 2 Fermi arcs. So you can see that from the low frequency to high frequency, these 2 Fermi arcs start to rotate around to form a spiral structure and then form this double helicoid Fermi arcs. Okay? So imagine about this. If you increase the frequency, this band structure will start to rotate around. Okay? It's like a DNA structure. Okay? And then what is also very interesting for this kind of band structure is, I told you there will be surface states over there. So if you think of surface states as an incident wave, this is the crystal, this is the whale crystal, and then this incident wave made this interface. So you will start to refract into the surface wave on the other side, okay? And then at the same time, there will be reflection, of course. there will be reflection. So if you treat it as a reflection problem, then there will be reflection as well. But because of this band structure, okay, if you consider this as an interface, but because of this band structure, if you launch an acoustic wave in this direction, the refraction will be 100%. And then there will be no reflection there will be no reflection at all. And this refraction is very counterintuitive because generally, if you think of, let's say this is interface, this is media 1, this is media 2. For high school, we all know that, oh, there's a Snell's law, right? So if you have incident angle positive, then the refraction, the refracted wave should locate in the opposite side of this normal direction. But now you can see this refracted angle is also negative. So it goes in the opposite direction as the normal case, okay? So this is so-called negative refraction. And in this case, this is topological because there's no reflection at all, okay? And then because this band structure, this surface band structure can apply to all the surfaces. So this kind of topological negative refraction can occur for all the surfaces, okay? Or you can observe this kind of phenomena for all the surfaces, not limited to any special arrangement. All right, so that's all for my talk. Thanks.
Thank you, Professor, for your interesting talk. And now we would like to take some questions our audience has.
Suggest some applications?
So I have a question.
Yeah, okay, later.
For this acoustic system, how do you define the Baile phase? Do you take the wave vector in any bands and the eigenstate of any band and you vary across as per normal?
How do I define Baile phase?
So how do you calculate the Baile phase for any?
How do I calculate Baile phase? How do I calculate Baile phase? Okay, basically we calculated this Baile connection first for each band. According to, you see there's a formula there. Okay, there's a formula there. So yeah, okay. If you need more details about how to calculate this, you can refer to some books about.
It's just a small minor thing, but in your slides about the SSH model, you show the Z phase to be minus pi/2 and pi/2, but normally normally the Z phase are 0 and 1, right?
Yes.
It depends on how many times the eigenvector circles around the origin. So it's 0 or 1. So you show that minus pi/2 and pi/2. I'm just wondering if you calculate it differently for the
you mean different values,
system.
right?
Yeah.
Okay. How should I put it? Z phase is gauge dependent. Okay. So this, okay, I should say this way: the exact value of Z phase is gauge dependent, but the relative value of Z phase has a physical meaning. Okay. Right. So the exact value doesn't matter. The relative value, the difference. Okay, the difference makes sense. Right. And Prof Lee just asked, okay, what's the application for this, right? So one application, if you think about this one-way propagation, I think it's very useful because that means you can launch the wave, propagate to the left and not to the right. So I can hear you, but you cannot hear me. This is one possibility. Okay, so this is one-way propagation. So you can play with it to create a lot of devices. And another possibility, well, I have mentioned this corner states, so-called. Okay, I have mentioned that there's corner states there. This corner state has very stable frequency. So even if you disturb the other atoms there, it will not affect the frequency at this corner. Okay, this corner is very, very stable. So that means if you think of a sensor, okay, usually when you want to measure something at this point, you want to measure only one point, not the neighborhood. But in reality, whenever you try to measure something, you always measure the neighborhood. So it's an averaged value. Okay, it's an average value. But over here, I told you that here, even if you disturb the other atoms, doesn't matter. Doesn't matter. This quantum state is topologically so-called topologically protected. So it has a very strong stability in terms of frequency. So only when you directly disturb this atom, then you will start to shift. So in that sense, if you use it to build a sensor, it can be very precise. You can measure only one point, not the neighborhood. And acoustics is also very useful in microfluid devices. Yes. So if you think of a resonance over there, you can trap the atom. You can trap the cells and biological particles, so on and so forth, very robustly.